Welcome, everybody in the lecture hall who had the courage to wake up early and come here at 9 a.m. Hello, everybody on Zoom. Hello, everybody watching us from the future. So I'll continue on cloud storage, mostly actually getting into key value stores. I'll ask you a few questions too, but I have one thing to tell you before. Who has never seen a rack? Okay. This here is a rack. It's even written on it, rack E5. So if you want to come after the lecture, take a look at it. It's technically an audio video rack, but basically it looks exactly like this, what you have here. I wanted to just tell you that. All right, so let me now ask you a question. So we have mathematicians in here. We have other people who might have taken a discrete mathematics lecture in their computer science bachelor. So this is my question. Which of the following most generally designates a relation that is reflexive, transitive, and anti-symmetric? Is it a total order, a pre-order, an equivalence relation, or a non-strict partial order? Transitive means that if A is in relation to B and B is in relation to C, then A is in relation to C, that's transitivity. Reflexive means that A is always in relation to itself, to A. And anti-symmetric means that if A is in relation to B and B is in relation to A, then A and B must be equal. That's anti-symmetric. So if it's all three of that, is it a total order, a pre-order, an equivalence relation, or a non-strict partial order? Let's look at your answers. Oh, wow, that looks like a tie. Pre-order, that scared everybody. Okay. Total order, equivalence relation, or non-strict partial order. Okay, let me tell you. In fact, it's one of these cases that the answer with the least votes actually is the correct one. It is a partial order. So let me just briefly explain. A partial order, who knows what a DAG is, a directed acyclic graph? That is a partial order. That's what it is. So basically, you can look at the graph, you will see it's transitive, it's reflexive, and anti-symmetric. Well, technically, when you have a DAG, you take what's called the transitive reduction. For the DAG itself, you remove the transitive edges, but basically, it's represented as a DAG. A pre-order is the same thing, but only transitive reflexive. You don't have the anti-symmetry. Equivalence relation, it's when it's symmetric rather than anti-symmetric. It basically means that you put everything into bags, and whatever is in the same bag is in the same equivalence class. Total order is the same thing as a partial order. Well, it's a special partial order where everything is in relation to something else. That's basically the case where the DAG is a straight line. That is a total order. It's a special case of DAG. But again, remember, DAG, directed acyclic graph, this is what the partial order is about. You will understand later today why I asked you this question. So let's go back to the slides. It's taking its time. Okay, now. All right. So where were we? We were almost done with S3, right? So S3 is about this cloud storage where you can store objects up to 5 terabytes. It's a flat key value pair model. What I wanted to tell you is that there's different prices you can pay for it, and that all has to do with availability. You can pay more for high availability, meaning that you have more guarantees about the availability, or you can pay less. Why would you pay less? Well, for backups. Because for backups, you don't care if it takes a few hours. If you don't have access to it for a few hours and then get it, it's okay because you're so happy that you actually got back your data that you don't mind waiting for a few hours. So this is called Amazon Glacier. or glacier if you speak French, and then you pay less in the exchange of less availability. So you see, you have all of these compromises that you can make. All right. Now, what is going to often happen in this lecture is that I'm teaching you a concept, a kind of technology, but actually there's multiple implementations of it. This is the case here. S3 is one of the possible providers that you can get. Azure is another one. They also have something called Azure Blob Storage. Google Cloud also has it. They kind of look alike in the way they work, but there's a few minor differences. And now, quickly, the best way is to just compare them. So how does Azure Blob Storage compare to S3? Well, instead of bucket and object, in Azure, you need your account, your email address, if you want, so your account, plus the name of a container. That would be like a bucket, except that the naming system is unique to your account, not in the whole world. That's why you need your accounts to be more precise. And then a blob, which is the same as an object. In fact, the O in blob means object, right? Binary large object. Then in S3, as part of the API, you have the ability to upload an object into several parts, not in one go, because that for 5 terabytes, it might be complicated. So you can upload several parts of it. And when you have uploaded all the parts, then you say S3, I'm done. Now paste them all together in that order, and then you get the object, right? But that's only an API thing. In Azure, they go further because there's actually something called a block, where you can divide the objects into blocks, but that we'll study as part of HDFS. Azure is actually in between object storage and distributed file system, but this is why I'm not telling you about block this week. I'll do that next week. Then the limit of 5 terabytes is also different on the Azure side. In fact, on the Azure side, they have 3 kinds of storage, 3 different flavors. The one called blobs, is basically for data. If you want to store a lot of data sets, that's the one you're going to take. Append blobs is for logging. This is when you just append new lines, like a log at the end of a log. So this is append optimized. And here it's you can fit a bit less, but then you just start a new blob when your log is full. And page is for memory in virtual machines, right? So this is something that is a bit unrelated to what we are doing in the course, but they also have page blobs. Okay, but you see the idea is quite similar. You have an API and you can upload and download objects from the storage given an ID, which can be a bucket or an object or an account and container and blob. ID, right? It's, when I say account, container, blob, the 3 of them are IDs that identify an account, that identify a container, that identify a blob. For whom is that clear? Okay, then I have good news. In S3, we don't have the slightest idea how they did it because it's not published, but Azure actually did publish a paper in which they explain how Azure Blob Storage works. That's an optional reading that I added to the lecture if you're interested. It's very likely that S3 has a few similarities with it, but at least they tell you a bit more about the internals. For example, what they say is that they have these storage stems, which is a couple of racks, typically 10 to 20 racks, which gives you 30 petabytes of storage. That's going to be in one data center, and then they have plenty of them around the world. They try to always keep it between 80% of storage capacity because you know what happens, you start on your laptop when the disk starts to get full, you get error messages, right, warnings. So they always keep it below 80%. If it goes above 20% of capacity, they just offload it to somewhere else. Maybe they are going to buy more storage stems and spread the data to other places. Okay, and on every rack you have 18 storage optimized nodes. Basically, it's going to be a lot of hard drives in there. So this is what they tell us. It's very likely that S3 has also something in that sense, and they also replicate the data. That's something I'll come back to next week. You don't want to lose. How do you reach, this availability, this durability of losing only one object in 100 billion per year? You do it by replicating. And the way is that they do it is that they store the same data multiple times in the same storage steps. That's called intra-stepped replication. That's done immediately. You upload an object, they immediately store it multiple times in the same storage stem, like here. And they also replicate it to another stem somewhere else But this is asynchronous. That means that they don't make you wait. You've just uploaded an object. They confirm that it's uploaded and replicate it here. And later, in the background, after you're gone, they will further replicate it to another step. That's the difference between synchronous and asynchronous. Okay. Then it's distributed, as I said, all over the world. There are two main reasons for that. First, you optimize latency, because no matter where you are in the world, there will be a storage stamp not too far away from you. So you can download it from there. And the second thing is resilience to natural catastrophes. You can have earthquakes, you can have tsunamis, you can have many bad things that can happen. Fire in the data center. I think it happened in Eastern France a couple of years ago. There was a fire in a data center. And they did not replicate the data to other storage stamps or other data centers, and businesses actually lost their data in the process. So that was a reminder that you really, really need to copy over and replicate the data over multiple locations. Okay, so this is blob storage. I'm not saying more about that because that's, again, very similar to the idea of S3. Which brings us to something slightly different, key value storage, which is also a kind of cloud storage, but I'm going to contrast it to object storage. So it's the same idea that we store objects that we call values, and a lot of them, very large number of such values associated with keys. So the problem is that if you just use S3 as it is in order to store data, or maybe have a database system on top of it, it's just too slow. Because for a database system, a couple of 100 milliseconds is too much. This is way too much. What you expect from a relational, from a database management system, relational or not, is just a few milliseconds. 2 milliseconds, 3 milliseconds, when you just do a lookup, this is your expectation, right? So cloud storage is a no-go for efficient real-time data querying, right? It's very good for analysis, right? When you want to query petabytes of data, and that's what we will do with MapReduce and Spark, but it's not good for a database where you need immediate and quick access to the values. For this, we have to find another solution, right? Again, typical database, few milliseconds to access one value. Which is why we have key value stores. In key value stores, we basically have the similar model of key values, right? We associate the objects with IDs, but the objects are going to be smaller. Instead of being 5 terabytes, it's up to 400 kilobytes, right? So you really store small quantities of data and not bigger things, right? By the way, the sort of things people store in these 5 terabytes on S3 is going to be pictures, it's going to be movies, like the pictures you upload to cloud services, maybe that you have on your smartphones. This is typically stored in S3-like storage. This is that kind of storage. You might also have videos and even chunks of videos. In fact, Netflix and Disney Plus and all these services, they are stored in S3, Azure Blob Storage, and that kind of storage. What it does is that your laptop or your TV or your smartphone just keeps downloading objects from cloud storage, which is a few seconds of your series. And this is how it switches. If there's not enough bandwidth, it's going to download objects in lower resolutions. So you have multiple objects in different resolutions. And then you switch dynamically between high res or low res, depending on your bandwidth, right? So the streaming systems, when you watch series, this is how it's implemented. It's on S3 blob storage, typically all of them. They don't even stick to one provider, but it's very common if you look on your firewall with Apple, for example. If you go to iCloud and so on, sometimes, I don't know if it's still the case, but you could see that it connects to Amazon IPs or Azure IPs, because it just spreads it to multiple providers. Okay, but in key value stores, we don't store series or videos or pictures and so on. We just store data, smaller amounts, 400 kilobytes, for example. Okay, so that's how it's going to differ. And of course, the implementation is also going to be different because the objects are much smaller and we can make it also much faster within just a few milliseconds. The API shouldn't surprise you. You basically have get, put, delete, right? So you can get a key, you can get the value associated with a key. You can put a new value associated with a key. You can also, I didn't put it here, you can also delete the value associated with a key, right? You could implement it on REST in a very natural way, right? Get, put, delete. These are also REST methods, but this can also be methods as part of a Python API, a Java API, you know, in any kind of API. So get, put. Well, in fact, it's slightly more complex because in reality, you have one more thing in there. You have what's called the context. When you return a value, you also provide a context. And when you put a new value back, you have to provide a context as well. But I will explain why. And that has to do with the question I asked on the DAGs and the partial orders. Okay. So now we have to make a few compromises on the system, and that has to do with the cap theorem that I told you about. There's a partition, a network partition. Either you remain available or you remain consistent. Cannot be the two of them. And this is exactly what people have been doing for key value stores and also for social media and so on. In order to accelerate the whole thing, we give up consistency. It's fine if the data is not exactly the same everywhere. It's eventually going to be consistent. If you give it enough time, at some point the data is propagating everywhere, but you don't stop the system until it's consistent. You allow for returning inconsistent values. So this gives better performance, it's much faster, and it's more scalable when you do it this way. So this is one of the tricks in big data systems, that we give up the consistency because we want to remain available. Okay. Now, in key value stores, the model is the same as in object storage. In fact, it has a name. It's called an associative array. In terms of abstracts, in the abstract type system, it's a map, right? You know, abstract types, set, map, list, and so on. These are abstract data types. Well, here it's a map. An associative array would be an implementation of that, right? You can implement it as a tree map, as a hash map, right? There are many ways that you can implement it. But the tree map or the hash map, that only works if everything is on the same machine, on your laptop. Then you can use Java libraries that take care of that. But the problem is that we have here so much data that we cannot implement that just as a hash map or a tree map on one machine. That doesn't work. We have to find another trick. Because we have a few requirements. First, we need to be able to spread it all over in the machines in a cluster, up to 1,000 machines, if you want, in the same cluster. We also want some guarantees that if we add machines, can we add a machine? Computer? Yes, this is one more machine. It has to continue working. That has to seamlessly add the machine to the available machines. And if you remove a machine, then the system also should continue to work, right? So it has to be dynamically adapting to the number of machines. Machines come and go, and the system continues to work, right? So that's the first requirement. Then we have another requirement. I think this is starting to strike. So let me be closer to the machine. So another design is that it should be symmetric. So all the machines basically run the same software and have exactly the same role and behavior. It has to be decentralized in the sense that there is no coordination node that everybody communicates with. It's just fully decentralized. And it's heterogeneous because the machines might not all be the same. You can have machines with more memory, with more CPUs, and other machines with less memory and less CPU. Well, in fact, now we know a system that has all of that. That's the blockchain, right? When you for the cryptocurrencies. So this is basically the same kind of requirements. But in the blockchain, that's the difference with this. In the blockchain, you have the additional requirements that you're also resilient if there are bad actors. Like you don't trust all of the computers, anybody can join, and you have to also be resilient against that. So the difference with the blockchain is, for this, you control all of the machines, and you know that you can trust them. This is all in your data center. There's a firewall, so you don't have these issues. Okay, so this is basically a peer-to-peer network, as opposed to the centralized architecture that we'll see in the coming weeks in big data, right? It's the only peer-to-peer architecture we'll have in the lecture, actually. So what happens in order to know which machine stores what is that we take the keys and we hash them. Who knows what a hash is? A hash function? Okay, it's a way of producing a string of bits, a sequence of bits from anything, right? That's called a hash. And hashes have it's basically from cryptography. if it's designed well, they don't collide so often. So you rarely have two values that would be hashed to the same one. Plus, the other aspect is that they're hard to invert. So it's very hard to find a value given a hash. Do we have a question on Zoom?
So the question is there a threshold for how many machines are allowed to leave the system or join at the same time for it to still count as incremental stability? Obviously, if all of them leave, it won't keep working, but also 90% of machines leaving the system wouldn't be ideal. So is there a general line?
Yes, I would agree with that. So these are not details that I go into also because I'm not a specialist of the implementation details, but you're absolutely right that, for example, imagine that suddenly 99% of the machines leave at the same time, then you are in a bad situation. It could be put in perspective with parameters of the system, N, W, and R, that I'm going to give you a bit later. But this is indeed the case that you expect that not too many machines are going to suddenly leave at the same time, because as you can imagine, you can lose data if you lose all the machines that's stored. Yes.
Or that key value stores, or at least a Dynamo, there's a limit of 100 kilobytes for the object. Is this like an implementation limit or is it a conceptual limit?
So I'm going to give. I'm going to give you a general answer that is going to not only apply for Dynamo, but also in general. I think that it really doesn't want to work anymore, this one. So generally, these limits that you put are basically a design goal. You want to optimize your system for a use case. So if you see it as a design goal, it basically means that as long as you respect this limit that it's below 400 kilobytes, your system is going to work properly. This is basically it. There's similar limits for document stores and so on that I'll come back to, MongoDB and so on. Basically, then in a system, you can have two different implementations of that limit, a soft or a hard implementation. The hard implementation is going to not even accept anything beyond that. And you say, no, sorry, I'm not doing it for your own safety, right? I'm not accepting these values. There are other systems that have a soft limit in the sense that they say, this is fine, I accept it, but this is at your own risk. And be careful because I'm not going to give you a warning. So then it puts the burden on you as a user to be careful. And in practice, you see these two kinds of systems. You really see these two kinds of systems.
Just the loss of guarantee.
Yes, exactly. You just shift the burden to the user and say, I'm not going to check that. It's at your own risk. And that will be the case. For example, in the case of MongoDB, it's going to throw an error and not let you store documents that are too big. But if you take HBase, it's not going to complain, right? You can use it with larger values. It's just going to be slower and potentially lead into issues, right? Now, DynamoDB, I don't know. I would have to look it up if it's a soft or hard limit. But whatever it is, there's other systems than DynamoDB that implement that. And probably some of them have a hard limit and some of them have a soft limit, right? So it's really, you have to understand it as a general design principle, right? Does it make sense? Yeah? Okay. All right, so now I'm going to go back where I was. Yeah, so we hash the values into strings of 128 bits, which is 16 bytes and not 7, as somebody made me aware in the notebook. I will fix that. So 128 bits per hash. And the idea is that visually the hashes basically can be seen as numbers that are no longer than 2 to the power of 7, if you want. And so basically, you can see it as a ring if you take the modulo, right? As soon as you have 128 ones, then you go back to all zeros. So you basically see that as a ring. Then what's going to happen is that for each machine that you have in your system, you play a lottery. You just pick a random place on the ring where the machines are going to land, right? So every machine generates a random sequence of bits, and that puts them on the ring. This is a logical view. It's not physical, right? Physically, it's a peer-to-peer network and the machines just talk to each other. At a logical level, you can visualize every machine as having a position on that ring, random. If you have a lot of machines, it's going to be more, you have an expectation, it's the central limit theorem, that it's going to be more or less evenly distributed. Of course, if you have less machines, then it can be more irregular, but I'll come back to that. Now that you have that, that determines who stores what. Basically, this machine here is going to store all the key values such that the hash of the key is here on the ring. This machine stores this machine stores this, and this machine stores this. Is there a question?
Does the logical randomness introduce latency in the physical propagation of data?
That is a good question. If you compare it with not being random, but being regularly put on the ring, it's only my intuition. I don't have the feeling that it would make a difference in latency. If you exactly distribute them or take it randomly, I think the reason for randomness is mostly that machines can come and go. And so if they can come and go, then it's easier to just put them randomly on the ring. So my intuition to answer your question is that I don't think it would have an impact on the latency of the system. And that's because all the machines talk to all the machines in a peer-to-peer network. Does that make sense? Just my intuition. Yes, okay, awesome. Okay, so now you know who stores what based on this. Yes, we have a question over here. Yes, that's a good question. The question is, can we have symmetry and heterogeneity at the same time? Yes, because heterogeneity is about the hardware available on the machines, memory and CPU. Symmetry is about the fact that they run the same code. So you can have the same code running on machines that have different memory and CPU. That's why it's slightly different, but it's subtle. Okay. There's another question. Yes, we can try also with this microphone. I don't think so. Let me. If there's volume in here, I can control.
So just to clarify, apologies if I missed this, but so does this ring represent both like the modular nature of like the hashing of the keys, but also the topology of the network of these machines? Like they only communicate in this ring of the next thing?
So this is purely logical. This is purely logical, and that decides who stores what. This is what it does. The topology of the network is a peer-to-peer network. Every machine talks to every other machine, even though, of course, it will be influenced by what they store. But the idea is really that this is a logical thing, the ring. Yep. Oh, it means that the fact that it's logical means that when you see this ring right here and the edges between the nodes, that's not network cables. It's only a mathematical visualization that allows you to say that a machine like this one is going to be storing the key values that have a hash that basically is between this value and this value. This is what this means visually, right? But the network cables are all over the place.
Like 1 o'clock, it doesn't have to communicate to the machine like past 3 o'clock. It's just actually trying to reach 5, for example. Like it can just directly, like for consistency or something, it can directly go to the one I have.
Yes, this one can communicate with everybody, but it might more often communicate with this one, but it's going to communicate with everybody, even 9 o'clock. Yeah. We have another question, 2 other questions. One over there. I think the microphone, I'm not sure. Can you hear the questions on Zoom of the students, or should we repeat them? You cannot hear them. Okay, so I'll have that in mind. So that's almost a cryptography question. So a hash, basically, to simplify, is basically something deterministic that looks random, if I simplify it. It's deterministic because typically it's going to be a bit of multiplication and addition in a modulo, typically when you implement them. But the thing is that it has to look a bit random to be unpredictable and very hard to hack, right? So cryptographically. Now what it means that since it has an implementation and you compute the hash in a certain way, in a deterministic way from the key, it's almost guaranteed that it's not going to be perfectly uniform. It's almost guaranteed because there's a bit of imperfection in reality. It's just that if it's a very large space and it's a very, very good hash function, we call that an ideal hash function, then it gets very close to being uniform, right? But there's always the math, and then there's the implementation that is never quite perfect. For example, you want hashes not to collide. In reality, they can collide. Right? Does it answer your question? Okay. And there was another raised hand. Where was it? I don't see it anymore. Oh, yes, over there.
Why is it exactly that? So if we're just talking about admitted responsibility, then we're assigning to this computer a certain range of IDs that's going to store all. Why would it then be more likely that that computer would communicate with the adjacent computers of the ring if there's not necessarily any responsibility with it?
That's going to come soon. I'll explain. It's on the slides that follow. Yeah, that's a good question. That was basically about why would they have to communicate with other nodes if they're just storing what's in their domain, right? But that will become very clear, right? So basically, if I continue to explain here, if you add nodes, for example, you add a node, that's basically, this answers your question too. What happens is that now this new node takes responsibility of this, while this remains under that responsibility. So in that case, there will be a transfer. All of the key values here will be transferred from here to here, because this one now is responsible for these values, right? So this partially answers your question. Now, so you need to transfer between nodes. So this is why these two will communicate then, because of that. Now, if you remove, these nodes are not affected. If you remove something, for example, this goes away, then you have to transfer back. Right? So let's assume it's not a crash. It elegantly leaves and politely warns that it's about to leave. Then this node is going to transfer these key values to that one before it leaves. Right? So this is what's going to happen. Like this. This is transferred here. But as you can imagine, that doesn't work if it's a crash, because if it's a crash, then you don't get any notice and you lose the data. So how can we solve that? Well, you might have guessed it's a bit with redundancy. What happens is that now, instead of storing only the key values that are right before you in the clock, you actually store two regions before you, right? So this computer stores these key values plus these key values. And that gives you redundancy, because now this machine stores these ones plus these ones. So it means that the key values here will be stored at two places. They will be stored here, and they will be stored here. For whom is that clear? So we introduce a bit of redundancy. That is also an answer to the question you asked, because it means that these two machines will kind of communicate with each other or interact in a way because they store the same data. That's also the reason why machines will tend to talk more often to their neighbors, but they can also speak to any other machine. Yes, over here, question.
I don't know which computer I need to talk to, right? So where's the table stored where I can look up which node is gonna be responsible for which data? Is there like any? Am I just gonna go randomly ask one of those nodes and ask them which node is responsible for the data that I want? Or is that like special node that I talk to?
So the question, I'm repeating for everybody to hear also on the recording. The question is about how do we enter the system? You want to query data, where do you connect to, who is in charge, and what phone number do you need to call, basically. So indeed, there is somewhere some sort of structure that allows you to know who is responsible for what. Actually, it looks like this. It's called a preference list. So this is a structure for every key or key range that gives you the list of nodes that are responsible for it. That's called a preference list. The way it's stored has to do with the distributed systems algorithm. So the same sort, do you know Paxos or the blockchain, or you know all of these kind of technologies that are outside of the scope of the course. But basically, there is a way to store data in a way that is organized in a peer-to-peer network that everybody shares the same data. Right? That's exactly how the blockchain works. You have many machines and they all have the same data, and there's a protocol that allows them to synchronize this data. It's called gossip protocols. One example. Does it answer your question? Partially, because the other part is who do you talk to? And the answer is any node. You connect to any node and that node is going to redirect you to the right one. Right? I have a slide on that. That's coming. Right? So we can connect anywhere, and then that machine will figure out who to connect you with, right? So just to finish that, there's a duplication of 2. You can also have a duplication of any number, 3 in that case, 3, 4. So you can pick your replication number, right? And then what you would expect is that the number of nodes in this table, in this preference list, is your target number, 2, 3 more. That's what we call n, right? So you have this list here. This is the structure that you have distributed systems algorithm that allow you to make sure that all the nodes have a shared view on that structure, right? It's not stored on a central drive or anything. It's really a protocol that allows everybody to agree on that common structure. Okay? And so basically you have these parameters that you have a number R. That is, when you read data, how many nodes do you need to get this data from to basically rely on it? Then you have W that says when you write data, for how many nodes confirmations do you wait until you consider that your data has been written? That's the number W. And N is the number of nodes that store that are in the preference list to store the data. And you have a requirement that R plus W must be more than N, right? That gives you some guarantees. I'm not getting too much into it. It's explained on a high level on the Dynamo paper, right? But basically you have this number N of nodes in the preference list, and R and W, which are the requirements for reading from R nodes and writing to W nodes. So now this is the answer to your question, actually, on that slide. If you connect to the system, typically first you're going to have a load balancer. So when I say you connect randomly, it's assigned to you. It's like when you connect to a website of a bank or Amazon or whatever, you have a load balancer that kind of directs people randomly to all the servers that can handle the request. So you have a load balancing system that assigns the visitors or the users to random nodes. And then the people who want to query key value pairs connect to one of the nodes that they got from the load balancer. And that node is going to figure out who is in charge by looking at this list that everybody has in the network. So they take the first node in the list, that's the coordinator node. And then you will also look at n-1 more nodes when you actually look for the data, right? And you stop when you have R of them that responded. For whom is that clear? Right? So you connect to a random node, and then that node is going to figure out who is in charge. Okay? Now, there's a few limitations to what I've just showed you. So one of the limitations is that you can only look up. You cannot do any ranges, for example. You cannot search. You can only look up if you know the key. Then it doesn't handle data integrity. It doesn't handle security issues. I told you that's the difference with the blockchain, that you have to really trust all of the nodes. But it's highly scalable, can work on many machines with really a high number of key values. It's robust against failure. It's self-organizing and so on. We have a question, I think, on the...
Why can't the load balancer just connect to the coordinator?
That is, yes, indeed. There are multiple designs possible. So this one just randomly assigns the nodes. It really depends on your system, because depending on the, when you look at the theory, it feels like everything is uniformly distributed, right? But now you go to a real company that has a real website, that has real people doing real searches on their websites. What's going to happen is that people have patterns. There's going to be words or searches that people do more often than others. And that means that you will have what's called hotspots in the ring. There will be places that are more solicited than other places because they're more popular. And so if you always connect to the coordinator, you're going to overload a part of the data center of the cluster and not the rest. By putting random nodes, you're distributing the work a little bit more when you enter it, right? So that's the reason. Does it answer your question? Yes, there's another question here.
I apologize if I missed this explanation earlier, but I think earlier we said that this network is sort of, or this database is decentralized, but here we have like a central coordinator, like sort of deciding like ultimately where some of things up. So I guess how does that relate to
So first, never apologize for asking a question, because this is a university, we are here to learn, and it's very likely when you ask a question that many people have the same question. So it's always totally fine to ask questions, and that's a good one, because indeed it feels here that this is centralized because we have a coordinator. But the reason it's not centralized is that there's a coordinator that is different depending on the key you're looking at, right? So it's really, this job is distributed. It's like in the TA team, for example, we have a TA of the week who is in charge of the current exercise sheet, but that doesn't make them the head TA because every week it's a different TA who is in charge, right? So that's kind of the idea. It's not the same coordinator for every key. Okay?
Like a Monty Python holy grail, like every week you elect a new leader or something.
Yes, exactly. And there's protocols for that. So there's this is one of them that's called Quorum. Then in distributed systems, there are lectures by Roger Wattenhofer. If you're interested, he teaches that very well. Also, he talks about blockchain and these things, explains that really well too. We have another question here.
Is the coordinator deterministically chosen for a piece of data? Is it like it'll always be the first?
Yes, it is deterministic because of the hashes and because of the placement. Once you have determined the position on the ring, it becomes deterministic.
So is that deterministic choice standardized as part of the architecture, or are there different ways?
It is standardized as part of the protocol. Yeah, so the idea is that once you have chosen the position on the ring, so that part is random, but once you have chosen the position in the ring, it becomes deterministic. However, it will depend a little bit on the failures of the nodes and so on, right? Because it's fully predictable if no crashes happen, but when the computer starts crashing and not behaving optimally, then it becomes a bit less deterministic, but it still works because it's resilient, right? By the way, I have an animation to show that to you, how it actually works. I'm not sure I will be able today, but I will have an animation that shows you exactly what happens when you insert and update the keys and the communication through the ring, right? So you will see it in action, and probably that's also going to help to make you understand. Still have a few more minutes, maybe I can say a bit more. Yes, what I want to say is that we still have a problem that, for example, you might be out of luck if you don't have a lot of nodes and then it's not evenly distributed, kind of addresses the question you had. And maybe you have so much heterogeneity that even if it's evenly distributed, it's not fair because even the large computers still have the same amount of storage that they're responsible for. The answer to this is virtual tokens. You basically create maybe 10 times as many tokens as machines, or 100 times, I don't know, maybe 10. And then you assign the tokens to the machines. Like this, I put colors in there. So you have 6 machines here, but you have more tokens than machines. And every machine is responsible for tokens. So the tokens replace the machines on the ring. Now we put the tokens on the ring and we assign the tokens to the machines. And this machine, for example, is responsible for that range, and plus more if it's duplicates. So now when machines leave, you just reassign the tokens to other machines, right? So you basically just decouple the positions on the ring from the machine, right? So these are called tokens. Okay, does that make sense? So this is how we artificially increase the number of positions on the ring. 2 questions, yes? Yes, they have to signal that they're going to leave, and they have to make sure to send data to other machines, but not necessarily, because even if there's a crash, since we replicate now, even in case of a crash, even if they don't communicate, it still works. It's still resilient against that. But yes, if they nicely leave, then they will communicate with the system, right? And it's really with everybody they communicate via this core protocol. Yes?
Does this architecture allow, for example, when a few tokens get hit by more traffic, does it allow for dynamic reassignment?
That is a good point. So basically the question is, what happens if there's hotspots, basically, if some of the data is accessed more often, then you can just reduce the distance between tokens. You know, you have ways of modifying it. I don't know if they did it in that system, but you can also dynamically adapt if you want in the design. That depends on your usage. In some systems, for some companies, maybe it's evenly distributed. For some others, it's always the same places. And for other companies, it depends if it's Christmas or if it's the summer, right? That really depends.
we never change the responsibility of a machine?
It's really dynamic. You can change the link between machines and tokens, and you can change where the tokens are located. That's one possible design, right? So thank you very much, everybody. If you have more questions, we can talk offline. I'm going to continue and finish this lecture next week. Have a good day. Enjoy the exercise session on SQL. Bye-bye.